And welcome to our webinar on the experimental and computational characterization of the effect of process parameters on strength and porosity of aluminum Si10Mg on an LPBF platform. This work is the joint effort by AlphaSTAR Corporation and Pennsylvania State University under the auspices of the NCDMM and MTTG. This work was also presented at the most recent AICME International Conference on Additive Manufacturing. My name is Rashid Miraj. I'm your presenter today. And if you're interested in AlphaSTAR, please visit our website at alphastarcorp.com. Our agenda today will address the state-of-the-art in AM heat and fluid flow modeling, a brief description of that, our physics-based approach, or our approach to that same challenge, and the results of the manufacturing process, tests and predictions, a summary of our methodology, and some conclusions. Within that, we will also describe case study and the results of predictions versus measurement, generations of process maps, density maps, void predictions versus XCT analysis, grain size predictions, and stress curves. This is the state of the art in AM heat and fluid flow analysis. There are a lot of low analytic and high fidelity CPU intensive codes that are available for heat analysis fluid flow calculations as related to AM. And they are being found in numerous tools that are out there that are being used. And as you can see, that not only can give you a sense of what is the morphology of AM structures, predicting morphology, they can also predict solidification process. The tools have varied capabilities, and many of them are mostly in scientific codes. Few are working their way into commercial products as well. And they can solve thermally driven as-built effects and defects measurements and understand both microstructural alterations and ultimate impact on build quality. Now, AlphaSTAR also has its own approach to this process, where fundamentally we're looking at material modeling of the system, understanding nonlinearity, temperature-dependent phenomena, and that begins with that thermophysics analysis for the particular composition of the material. What are the factors that come into play? Power, speed, AM process parameter configurations, how those process parameters impact that material model. Next, we consider not just toolpath or macro effects, but the implementation of the G code, because that's ultimately the driver of process parameters. And so while you may have a sense of what process parameter A or B might do at a particular moment, when you compound that over time, you get a sense of the generation of defects and potentially the effect of those defects on as-built material properties and ultimately on the fabrication of the part itself. So again, all that information on the material model as well as temperature distribution through the part as related to the G code, temperature distribution over time, is mapped into a mechanical model and subjected to the thermostructural analysis with the help of a finite element toolset. With that analysis, we can then predict distortions, net shape, warpage, shrinkage, other parameters that are related to as-built part quality. And in addition to that, our tool set can take that virtual as-built part, subjected to in-service loads, to see as-built or as-is part performance. So ultimately, process simulation can take you down the road to the analysis of the as-built part. So let's take a look at some of those results. And again, the research is ongoing, and we will have more detailed results in the future. This was the input materials of the aluminum Si10Mg system, alloy, provided by 3D Systems and utilized by Penn State University. You can see the basic composition on the left, as well as density and other considerations, and then the properties of that material as provided by 3D Systems, including in the center a sense of what the microstructure looks like That's as built and then after some post-heat treatment as well. Well, this was the input we used for our simulation model. Again, you can see considerations related to process parameters on the left, composition on the right, and in terms of more detailed understanding of the material, the packing, powder packing, the size of the powder that was involved in the simulation itself. And so we take into consideration composition for the process model, and that's what we use to determine the melt pool, thermal conductivity, density, and other considerations. This is showing the results of the temperature time history of the LPBF process. As you can see, the thermal states, including the melt superheating, superheated cooling, solidification, cooling, are incorporated into the analysis, and that initially with, say, the material composition gets a sense of what should happen, and then when you throw in the actual G code, temperature versus time, a particular build plan, then you can predict defects as related to that material system. So here we're able to look at the evolution of the melt pool, in this case the aluminum Si10Mg on the 3D systems platform. And it's, of course, melt evolution over time. We were predicting the length, width, depth of the melt pool, and we are also comparing that to actual measurements. In our case, we've done work with multiple laboratories and been able to get good validation of our prediction systems. And along the way, we're also predicting the applied volumetric energy density, so how that impacts the actual melt pool dynamics. One of the first criteria of utilizing material systems is getting a sense of what are the stable and unstable build regions, which are a function of the process parameter settings and the particular material system as well as the platform itself. On the left, you can see the experimental work undertaken by Penn State universities to develop that process parameter map. They prefer to use 3 identification codes or keys to describe stable, unstable build areas. And on the right, you can see the predicted process map generated by our ICME toolset. And we happen to use a 5-category system to describe those stable and unstable build regions. But overall, if you compare the 2 systems, you can see there is good agreement in general about what is the stable region and what is not, or what is unstable in terms of process parameters related to the build. So you can see the utilization of such a tool, so such a product, can help you define what are the first assumption process parameters that you need to use to minimize defects. The same process or same analysis can be used to predict lack of fusion in the process parameters. So in the upper left, you can see we're comparing volumetric energy density versus lack of fusion. From there, very interestingly, we can generate what we call our virtual carpet plot, extracting that analogy from composite systems. But the idea being that what combination of volumetric energy compared to a percentage of defects, what can you do to find the sweet spot or the ideal energy density where you are not suffering from lack of fusion, but you're not accelerating the presence of defects or potential anomalies that can affect not only part net shape, distortion, warpage, but ultimately impact part performance. So the tool set can allow you to predict the ideal density setting to minimize or mitigate potential anomalies. And so the process map can also be generated in terms of lack of fusion, as you can see the on the up half, and then also, if necessary, a density map for estimations of density related to the power process parameter settings. On the right side, you can see comparison of prediction versus test for certain power speed settings, both in terms of, in this case, a fixed hatch rate setting, and the temperature predictions and the process parameter configuration showed good agreement between test and simulation at various speeds and at various system configurations. Ultimately, lack of fusion or simulation versus test was taken from the literature. Hopefully, we'll complement that with more physical tests as this joint research effort continues. And this is, again, a lack of fusion and energy density is a critical phenomenon, critical point of understanding for AM process fabrication. Well, our overall thermo-physical analysis, the inputs assumptions to go along with that, in this case, we utilized the dog bone, first the overall dog bone, which had a fixed computational time for analysis, and then an overall quick analysis based on the first 50 layers of the specimen. Our bulk of the work that you'll see today is based on that initial 50 layer assessment, but the continued research will take on the full dog bone analysis as we move along with this research product. You can see on the left-hand side what were the critical inputs related to this analysis, touching base with things that most people would normally expect: laser power, laser diameter, scan seam, absorptivity, thickness, bottom plate temperature, including bottom plate initial temperature, and in addition to the material system, and chamber temperature, assessment, initial porosity guesses. And so we were able to undertake this analysis of the various process parameters and use that to determine temperature-dependent material properties as impacted by the build plan and the tool path. Here's a prediction of voids versus physical test measurement. Void distribution versus, again, as a function of the process parameters at a fixed hatch space specification, comparing our simulation versus physical measurement. And first cut analysis on the 50 layer specimen showed reasonable good agreement. Remember, the test data is taken from the full test build with a specific location in mind, and we were showing general behavior and patterns that come up with the analysis of the tool set. In this case, you can see variation of the density void distribution through the 50 layer part. And that over time, versus time, you can see it leads to a specific or more stable estimation. And then this was just, again, that lower 50 layer. As the analysis continues, we'll be comparing it to the full specimen, as noted on the left-hand side, where that particular measurement was taken for the test analysis. With additional research, additional analysis, improved calibration, the toolset will be providing the more accurate assessments to give you confidence to move forward on the overall part. Here's an example of grain size prediction. In this case, again, versus the literature. We are getting initial test data from PSU. They're yet to publish their work, so once they have got their stuff ready to go, we'll be then able to compare our stuff in the literature, hopefully in our next presentation round or next set of webinars. As you can see, there's a fixed temperature at which the analysis is taken for those 50 layers of that initial level build. Grain size predictions for the material system, which ranged distributed over a fixed range, and actually the physical measurement in the test literature, and ours kind of spiking at a specific point. As you can see on the right side, it's showing the types of grain size from the literature. There's a kind of distribution there depending on the temperature. And overall, our analysis showed good agreement with the literature, especially with the understanding that time factors come into play and you get more stable grain size as cooling and takes over. And so the whole point is that you can actually predict the grain size, which then allows you to apply methodologies to optimize and drive the grain size to a size angle that is of specific interest to the end user. Here we're looking at the impact of hatch spacing, in this case on time temperature history, as well as void volume ratio. You can see the build is sensitive to hatch spacing as could be expected, but again, on the lower, smaller system, the 50 layer analysis, the full dog bone specimen will be upcoming. And not surprisingly, it has a profound effect on the melt, including the impact on grain size and other mechanical properties. Again, there we're looking specifically at the case of spacing on the grain size assessment. And so on the left-hand side, you have the void volume ratio in comparison to test, and on the right side, the grain size as experienced and tested. This is the PSU value in this case, and the change, what we're saying here is that again, where PSU took it as a specific location, we have that general distribution through the 50 layers, and again, reaching a stabilization point. Further analysis, further calibration will ultimately improve the comparison, and then we'll also be looking at a full build and looking hopefully at the point-to-point comparison between the two assessments. Here we're talking about the information that's gone into our material model, in this case using voids, air pockets as an inclusion, including shape, size, orientation that can come into play. And all of that information is used to get our as-built material properties. And then we can also sense of how the various process parameters may impact those properties, whether it's strength or some other factor. And as you can see, our analysis has shown that the hatch layer and layer thickness tend to have greater impact than, say, some other factors that come into play. Also, orientation is a consideration, but here we're looking at various power and speed settings with different void volume ratios. And as you can see that with those combinations, the tool set still provides good analysis, good agreement with experimental results. And not surprisingly, both porosity and residual stress lead to scatter in the analysis and into the stress strain curve. Overall, again, noting that our friends at PSU are yet to present and publish their work in their deference, we have normalized our properties to show agreement between test and prediction for both modulus and strength, and the similar analysis will be undertaken for strain and other critical material properties of interest to the AM community. So what's our overall methodology? Well, we hinted at that early on. We talked about the 7 pillars, we call 7 pillars related to AM process modeling and build optimization. It all starts with the Thermo-Physical analysis, which is that really detailed understanding of what is your composition and how it's impacted by various AM process parameters, and what would be the first cut of what could go wrong, what would be the defects with this combination of material and process parameters and ultimately temperature that come into play. And that's on a micro scale level, looking at voids, microvoids. And then the next step would be to bring in the print error management, which actually brings in the G code to understand how the specific build plan would impact that overall potential generation of defects in the material of choice, the composition of choice, given the process parameter variation, power, speed, hatch spacing configurations over time. And all of that information is what's fed into our material model. Now, we also have a component we call our grain boundary engineering capability, and that involves inherent in situ variations to the build plan of G code, thermal cycle, inherent heat treatment that can impact cooling, heating, thermal cycling, ultimately impacting grain architecture. That's an advanced technique, but it's a capability that is being under continued development. And again, all that information can be bundled into our analysis or modeling to understand an as-built material model over time, including nonlinearity for this particular build set. And so once we have full thermal distribution versus time, our assessment of material mechanical properties, we can then at its location over the overall build plan, over the G code, all that information can be bundled or mapped into a structural model for thermal structural analysis. And then with the help of finite element code, we can then assess warpage, distortion, net shape, questions related to quality of the AM build, including residual stress, residual strain, how that impacts on not only build quality, but in a further step toward as-built part performance. The toolset also provides you an opportunity to incorporate in situ data to revisit the analysis, update the analysis, or the toolset can work hand in hand with AM platforms to provide predictions of the upcoming layer to see if corrections are necessary. So for the available platforms, there's an opportunity for integration to supplement and add to the feed-forward feedback control to improve the quality of ultimately the builds. And one other component, being the seventh component, would be selection identification of machine parameters using optimization techniques. Could be advanced artificial intelligence or machine learning options. There are single criteria, multi-criteria methodologies inherent built into the system, baseline AI and machine learning tools as well as the capability for a user to add in any specific subroutine or capability they think would be necessary to look at the data and assess patterns to identify the ideal process parameter settings to ultimately mitigate anomalies that may arise as a result of the build plan or as a result of the fabrication process. And with those optimized process parameters, mitigate, eliminate those defects, anomalies, and the effect of those defects. And as you can see here, what we're talking about is our powder to part analysis, where we're taking into consideration the powder and also into the build environment, the temperature of the chamber, depending on if an inert gas is being used or not, and then being able to take that powder analysis, powder behavior to come up with our process map and see how the process map is affected by certain configurations of process parameter settings, ultimately leading to stable and unstable build areas, and which allows us to not only get a sense of what's happening, but ultimately predict the melt pool and understand the dynamics of the melt pool over time. And with that time element, being able to understand what would be an as-built stress strain curve of the component, not only at a particular location, overall through the part, or averaged through the part. And so all this information gives you an understanding of not only the defects, but ultimately the effect of those defects and how they impact part performance. Here we're looking at thermal conductivity versus defects. Again, additional information to help you understand what is going on and how certain behaviors, certain phenomena may be critical or may be driving these certain gradients, may be driving defects, and what can you do as an end user to mitigate it, in this case density, or mitigate problems related to other areas. And then tools that are on the way, again, in parallel with this overall project, PSU is looking at the fabrication of 60 simultaneous builds. We were utilizing the tool set to analyze both that minimized 50-layer initial build and then the overall dog bone. But the ultimate challenge we were chasing, which hopefully will be available very soon, is the analysis of the capability to predict as-built properties for multiple sets of specimens built simultaneously. So not only predicting that, but the next step, even more significantly, optimizing the process parameters so that all of the parts are built to the ideal build requirements, quality specifications required by the end user. And so a very large and technical challenge, but something the tool set is ready to take on. So in conclusion, the tool set, with the understanding of the thermophysics, the incorporation of the build plan and the macro behavior based on print path coverage and print error management, and then taking all that information and mapping it into a material modeling, feeding that into thermostructural analysis, we're able to not only understand the impact of, say, thermal analysis, endothermic effects, exothermic effects, triggering of inclusion or the impact of inclusion, so the triggering of precipitates, and how that ultimately impacts microstructure. All this is available through the toolset. Hopefully we'll present it in our next series of webinars, and that the toolset is there to not only predict that, but to optimize the process, and then ultimately with the optimization in hand, drive the process to particular outcomes. And significantly as well, tools that will allow you to take that as-built part with the flaws or with the flaws mitigated, take that subjected to in-service load and see as-built performance, and even to the next step where you develop a fracture control plan and understand fatigue life as is behavior somewhere down the lifespan of the part, subject to whether it's static loads, cyclic loads, whatever may be the case, but full fatigue life, residual life analysis and understanding. And all of this, as we said, was to not only predict, but ultimately improve strength, reduce porosity, and ultimately improve the quality of the finished part. Thank you for your time, and please reach back to AlphaSTAR Corporation if you have any questions.